All right, we're going to look at the regiochemical outcome of a Birch reaction when benzene contains a substituent. And the substituents can be categorized into two groups. We have an electron donating group, right? Now, when there's electron donating group on the benzene ring, so look at what happened. The carbon that have electron donating groups are not reduced. The carbon next to it get reduced, and the opposite, of course. But when there's an electron withdrawing group on a benzene ring, right, the carbon that have the electron withdrawing group get reduced. Yeah, how come though? That's very selective. All right. All right, we're gonna look at it. Why this happened? So we have to consult the mechanism. Okay. All right. So we're gonna draw the. I'm gonna draw this mechanism, and I'll have you see it to yourself. All right. So when this sodium donate this extra electron to a benzene ring, so two options could happen. There are two possibilities. The carbon on the right side, that red carbon, get a negative charge, and the one next to it become a radical and can do resonance structures, look like that. Or the carbon that have methoxy group on it become negatively charged. All right, and the carbon next to it have become radical and resonant. Ta-da! You get that. Now, tell me real quick. We have two resonance structures at the top and at the bottom. Which one do you think is less stable, and why? I'll ask you one more time. You got two resonance structures, two possible resonance structures here and here, top and bottom. One of them is less stable than the other. Which one and why? Well, the answer is this guy. Okay, look at right here. This guy's electron donating group. That's a high electron density next to it. A lot of electrons, a lot of electrons. Do they like each other? Not really, right? Methoxy group try to donate electron to the benzene ring with a lone pair, and this carbon right here in particular, already have high electron density. Basically, having an electron donating group right here is not a good thing. It would destabilize that negative charge. All right, this one by resonance effect. If there's a methyl group, so let's say we have a methyl group, this negative charge would be destabilized by hyperconjugation. Okay, so it's not good. Basically, the resonance structure at the bottom is less stable, slower rate of the reaction at the bottom. So the faster rate will be at the top. Okay, that's why the carbon that contain electron donating group don't get reduced. All right, that's the electron donating group. Now, electron withdrawing group. Okay, the carbon that have electron withdrawing group is get reduced. How come though? Same thing. We use a mechanism to explain. Again, you got two options. Have that carbon become negatively charged, and you can draw resonance structures. Or have the carbon that have that acyl group, we call acyl group right here. The carbon that have acyl group become negatively charged, and the carbon on the right side become radical, draw resonance. Okay, one of these is more stable than the other. Which one is more stable and why? This guy. Okay, this guy is more stable because high electron density. What does this acyl group do again? It is an electron withdrawing group. It pulls electrons, use a resonance effect. Okay, so stabilize that negative charge. We love that. The negative charge up here on this resonance structure is not stabilized. Right. So basically, the resonance structure at the bottom is more stable, faster reaction, and lead to the product that the carbon that has electron withdrawing group become reduced. Okay. Oh, let's guess. Okay. We're gonna do this Birch reduction. Look at this benzene ring real quick. There are two types of substituent on it. We have electron withdrawing group at the top and the electron donating group at the bottom via hyperconjugation, of course. Okay, so which carbon get reduced though? Of course, it's gonna be the carbon right there next to the electron withdrawing group, because the electron withdrawing group stabilize the carbon. Okay, and you have to avoid put the negative charge on that carbon because the electron donating group is next to it. All right, the mechanism goes like this. So put the negative charge on this carbon. All right, so that's what we're gonna do. The radical will go to the carbon next to it. Draw resonance structures. There we go. You have the negative charge right here and the radical opposite direction. Yeah. All right. Add on the proton. Use a solvent. Ta-da! You get one. Got reduced. The other one, we need to make this guy as a lone pair first. So take the another sodium, add another electron into it, you get a lone pair. Pronate with the solvent, and you get this compound. All right. I hope it helps a little to see how this works. All right. Last video, we're gonna do one synthesis problem. Okay.